There are 2 study sessions on quantitative methods. This is the reading on time value of money. Let's start with a quick definition of time value of money. Time value is really just the notion that money accumulates value over time. In other words, $1 today is not the same thing as $1 tomorrow. So if I gave you a choice between receiving $1,000 today and $1,000 at some time in the future, say in 5 years, you would clearly make the choice of receiving that $1,000 today because you can either spend it today, but even in the absence of inflation, you would prefer to have that $1,000 today because you can invest it today and earn interest over time. So that $1,000 will be worth far more than $1,000 in 5 years. Let's look at the LOS that asks us to interpret interest rates as 3 different measures of a rate of transformation. Interest rates can be thought of as a required return, a minimum rate of return that is necessary in order for an investor to make that investment. A discount rate is simply the interest rate used to discount future cash flows to compute a current value or a market value or a present value. An opportunity cost is the value of the best foregone alternative. When I think of opportunity costs, I always think of my time at the beach in the summer when I see all of these miniature golf courses. And I always ask myself the question, is that really the best use of this property? And I guess since there are so many of them, and that when you try to go miniature golfing, there are millions of people in line, I guess that is the best alternative. But the opportunity cost would be the opportunity cost that, let's say, a developer wanted to build an apartment complex or condos on that particular property, whatever interest rate that would be. So I guess the miniature golf course owners are earning more than the property managers down at the beach. All right, let's go ahead and describe the scenario under which a borrower and a lender agree on the terms of a loan. That interest rate has to be the sum of the real risk-free rate of interest plus other things that the lender requires compensation for. So what constitutes a given rate of interest? It's going to have several components. It's going to have the real risk-free rate of interest. There's going to be a premium for inflation, a premium for default, a premium for liquidity, and a premium for maturity. Let's look at each of those in the bullet points. The real risk-free rate of interest is the single period interest rate for a completely risk-free security if there is no inflation. The inflation premium, of course, compensates the lenders for the risk of inflation. In other words, if you come to me and say you want to borrow $100 and I expect inflation to be 10%, I'm not going to charge you just a 10% interest rate because I lend you 10 today, a year from now you pay me back 110. Well, my purchasing power is identical. I got nothing out of that loan. So there has to be compensation for inflation. There also has to be compensation for default. There are multiple examples out there, but let's take 2 that are personal in my family. You know, I'm 57 years old. If I came to you and said, hey, I want to borrow $100 for a year, you may pick an interest rate, let's say 5 or 6%, and that 5 or 6% is going to depend on the likelihood that I'm going to repay that loan, default risk premium. But if one of my sons came to you as an early teenager and said, hey, can I borrow $100? You're going to look at one of my sons and say, now wait a minute, you're 14 or 15 years old. How are you going to repay me this? I'm going to charge you something more than I would charge your father. Default risk premium compensates investors for the possibility that the borrower will fail to make those payments. Liquidity premium must also be considered. If I ask you for a loan for a year, you have to give up that $100 for a year. So think of all the opportunities that you will miss out without having that $100 over that 1 year time period. But if I asked you for that $100 over a 5-year period, then you have 5 years worth of missed opportunities. So you're going to charge me a little bit more on that 5-year loan than the 1-year loan to compensate you for liquidity. And then there's a maturity premium that will account for the additional risks associated with the longer term to maturity. Now, this is not liquidity. This is a time to maturity, and it has everything to do with interest rate risk, the variability in the value of that loan. Once we get to the bond pricing readings, we'll talk at length about duration and interest rate risk. The next LOS asks us to calculate, so we'll have to get out our calculators, and interpret the effective annual rate given the stated annual interest rate and the frequency of compounding. So let's go ahead and talk about two important things. Compounding is the process of earning interest over a period of time. So we take a current value and we add interest over time, and sooner or later we're going to add interest on top of the principal, on top of the interest, on top of the principal, until it becomes a larger future value. Now, if the number of compounding periods within a year is finite, that's called discrete compounding. But if the number of compounding periods is infinite, then that's called continuous compounding. The periodic rate of interest is the rate of interest earned over a single compounding period. The stated annual interest rate is an often quoted rate that does not account for the within the year compounding. A mortgage loan, for example. Those of you who have bought houses will have been told by the mortgage banker that the interest rate is 6% per year, but that translates into a different effective annual rate because of the compounding 12 times per year. Let's be a little bit more specific about this one here. What is the effective annual interest rate? And so the formula is a good one to memorize. Notice the effective annual interest rate is the 1 plus the periodic rate, which is going to be the standard stated annual rate over the number of periods. And then we raise it to the number of periods and we subtract 1. Let's go ahead and do an example here. Let's say we've got a stated interest rate of 10% compounded quarterly. All right, so in order to compute the effective annual rate, all we do is take the 10% in decimal form, mind you, divide it by 4, the number of quarters in a year, add 1 to it, 1 plus that interest rate, and then raise it to the 4th power because there are 4 quarters in a year. Subtract that 1 out. So, notice inside of the parentheses, we add the 1 so we can get the effects of the compounding, and then we subtract the 1 to get rid of those effects of compounding, so we're back into an interest rate. So that 10% annual stated rate translates into 10.3% if interest is compounded quarterly, and then 10.47% if interest was compounded monthly. And then we could go on. We could have interest compounded weekly, although that's not very common. We could do it biweekly. Some mortgages do biweekly. Bi-monthly loans and biweekly loans, but you could do daily. You could do by the minute, really, if you wanted to. And if you get down to every instant, that's called continuous compounding. So the more frequent the compounding, the higher the effective annual rate. Let's go ahead and get out our calculator, although we don't really need it for these simple examples here, but we'll need a calculator. Solve time value of money problems for different frequencies. So I have a couple of formulas there in blue throughout the slide. If we want to determine the future value of $1 after a certain number of years, all we do is take that present value and we multiply it by 1 plus the interest rate raised to the n power. So I have an example in green. If we start with $100 today and our interest rate is 10%, just multiply that by 1 plus the decimal form of the interest rate, raise it to the 1st power, and we get a future value of 110. Should be fairly easy to understand, fairly easy to compute. Now, if this were 2 years, we'd take that 100 and we'd multiply it by 1.1 raised to the second power, and we'd get $121. This is the beauty of compounding. We'd get $10 worth of interest and $10 worth of interest, and then we'd get $1 worth of interest on top of interest to get to that $121. Now, what we can do is we can then compute present value as as a function of the future value. And so the formula there is just rearranged. I learned it as product of the extremes equals the product of the means, but you guys probably learned it as cross multiplication. And so if you just cross multiply, you solve for present value, and present value is simply the future value divided by 1 plus that interest rate raised to the n power. And so back to my previous example, if we have a future value of 110, suppose I promise to pay you 110 a year from now, and the interest rate is 10%, I divide that by 1.10 raised to the 1 first power, and I'm back to my $100. So I want you to think of present value and future value kind of as opposites. They're not really opposites, they are reciprocals of each other. And that's the beauty and the effects of compounding. Now, when the compounding periods are other than annual, you've got to make some adjustments inside of the parentheses and then outside of the parentheses. And so I gave a quick example here back to my example at the top of the page. Suppose interest were compounded semi-annually. What we do is cut the interest rate in half, so it's 5%, so we have 1.05, and then we double the number of time periods because there are 2 6-month time periods within a year. So we have $100 times 1.05 squared, and we get $110.25. So you see the beauty of compounding. Back when we were compounding just once a year, our $100 grew to $110, but now that we're compounding it twice a year, our $100 grows to $110.25. And of course, that $110.25 would be greater if we compounded monthly and weekly and daily, et cetera, et cetera. Here's a good example. Let's suppose that we want $10,000 in our savings account at the end of 3 years. If we have a discount rate of 10% quarterly compound, how much would we need to invest now? In other words, what is the present value of that $10,000 to be received in 3 years if interest rates are 10%? And here's the formula, and we can compute that 7,435 just by making the adjustment. Notice we divide by 4, and then we multiply by 4. Divide inside the parentheses, multiply outside of the parentheses. Now in a few slides, in this slide, I'm going to show you how to make this calculation using your financial calculator. So let me go back to this previous slide. Do we really want to memorize that formula? Of course not. The Institute allows us to use 2 calculators, so we might as well get used to doing those now, early on in our studies. And so here's the thing. Notice across the third row of the BA2 Plus, there are what I call the 5 time value of money buttons. There's an N, there's an I/Y, there's a present value, there's a PMT, which stands for payment. That's going to be the annuity button, and then future value. And so here's the thing. What you've got to do is you're going to be given, almost always, you're going to be given 4 of those 5 inputs, and then you're going to solve for the 5th one. So let me just go back here. Notice what we're given in this problem. We're given $10,000, so that's going to be a future value. We want that at the end of 3 years. N is going to be 3 years. The interest rate is going to be 10%, and there's nothing in here about the payment, so we're going to make the payment 0. All right, so here are the inputs for the calculator. I will allow you to pause the video to make certain that you can compute that 7435. So in the previous slide, using the formula, we got 7435. And here, using both calculators, we get 7435. The next LOS asks us to calculate and interpret future values and present values of a single sum, an ordinary annuity, an annuity due, a perpetual annuity, and a series of unequal cash flows. Let's go ahead and start with some definitions. First of all, an annuity is a series of consecutive, equal payments. And there are a couple of different kinds of annuities. The most common annuity is an ordinary annuity in which the payments are made at the end of each time period. Think of your mortgage loan. Those of you who have homes will note that you went and when you borrowed the money, you had a settlement date, and the mortgage banker lent you the money. Of course, the money didn't really go to your hands. It went right from your hands right into the homeowner. And you agreed to make regular monthly payments that were equal over 15 years or 20 years or 30 years. And when did those payments begin? They began 1 month from the day that you settled. Annuity due, on the other hand, the due part, DUE, means that there's a payment that is due today. And this is common with a lot of insurance contracts. If you go down to your insurance agent and you want to take out a policy for your home or your automobile, the insurance agent will require an immediate payment. And if you pay it in full, then that's just a one-time lump sum. But if you pay it in increments, like I do, over quarters, then you pay it quarterly. And so you have to pay that first one immediately. So make sure you know the difference between an ordinary annuity, payments begin in one period, versus the annuity due. The due part means today. Here are some good formulas for present and future values of ordinary annuities. But remember, our calculator has a PMT button, and we'll be able to use that button to solve for present and future values of the annuities. There are some formulas for the present and future value of annuities due. But again, we can use our calculator. Let's take an example. Dave Maxwell buys an annuity that pays regular series of payments, $200 a year for 15 years. He is to receive those payments at the beginning of every year. What premium should Maxwell be willing to pay for this annuity, assuming 13.5%? Well, we get out that formula for the present value, and there's the 13.5%. Add 1 to it, raise it to the 15th power, and we end up with a present value of $1,430. Or we can use the financial calculator and hit those 5. Remember I said there are 5 time value of money buttons, and so we'll solve for that same. Let me go back here. There's 1430 and there's 1430. I'll let you pause the video to make certain you're up to date on the calculator steps. The next LOS asks us to demonstrate the use of a timeline in modeling and solving time value of money problems. I believe that if you craft a timeline accurately, the time value of money problem actually solves itself. If you can visualize the timeline, if you can go from a paragraph of words to a timeline, then you ought to be able to solve any time value of money problems. And so what do the bullet points tell us? It helps you visualize the cash flow. It helps you distinguish between equal and unequal amounts. And it's very helpful in solving present value and future value problems. Here's a good example. Suppose we have a series of cash flows. $100 at time period 1, $150 at time period 2, $250 at time period 3, $300 at time period 4, and $250 at time period 5. We're given an annual interest rate of 5%. The question is, what is the present value of that series of unequal cash flows? Now, here's the thing. These are not equal. They're consecutive, but they are unequal. So we're not going to be able to use the PMT button on the calculator. They do occur at the end of each period. So let's put together a timeline. So here we've got time period 0, 1, 2, 3, 4, and 5. And there is the appropriate dollar amounts for each time period. Now the question asks us for present value. So we're going to put the unknown, we're going to put the PV or the X, if you go back to your algebra days, we're going to put the X in time period 0. So what we're asking is, how much is it going to cost us today? What is the price today that we would be willing to pay to receive those series of consecutive unequal cash flows in the future? What is the present value? Well, let's go ahead and do it the long way. And the long way is going to take us through computing the present value for each consecutive future value. All right, so notice what I've done. The $100 received in time period 1 is worth $95.24 today. The $150 received in time period 2 is worth $136.05 today, and so on as we go in time periods 3 and 4 and 5. This is the long way to do it. And interestingly enough, on an exam, if the time period is 2 years or 3 years, there's probably not much time saved by doing it in a shortcut. But 5 years or 10 years or even 100 years, oh boy, then that takes a long, long time. So if you sum those individual present values, you get $889.94. However, there is a better way. Notice in the middle of the calculator, there is a CF button and an NPV button. And so it's much easier to use the cash flow function and the NPV function to do it. And I've given you the calculator steps for the Texas Instruments and for the Hewlett Packard. And I'll allow you to pause to get familiar with your calculator steps. Either way, you're going to get $889.94. Now remember, those of you who have the BA2 Plus, once you get into that cash flow, you have the ability to scroll back and forth. Here, let me do this. You have the ability to scroll back and forth from time period 0 to 1 and 2 and back to 1 and 2 and 3 and 4 and back to 0. And the way you do that is with the arrow buttons. So get used to those arrow buttons. So you're going to go down. It's not really a down, it's kind of a cross. Sideways, you're going to go down and you're going to enter all of your cash flows. Then, once those cash flows are entered, hit the NPV function, and then you enter the interest rate as 5%, and then you have to hit compute. Remember, you Texas Instruments people always have to hit compute something. And the HP is pretty simple too. And that completes our discussion on time value of money. Next up is discounted cash flow apps.